Hello, my name is Gedaliah Knizhnik, and I'm presenting the paper I wrote with Dr. Mark Yim for ICRA2021 titled Docking and Undocking a Modular Underactuated Oscillating Swimming Robot. The oscillating swimming robot we use is called the Modboat. This is a single motor swimmer that uses the conservation of momentum and two passive flippers to propel itself and turn. The unique encapsulation of the design allows individual modboats to dock together to form modular structures. You can see the core propulsion mechanism in this video here. The motor spins the bottom body relative to the more massive top body, and the oscillation causes the two flippers to open in a paddling sequence. This can be leveraged for both thrust and steering. By modulating various features of the oscillation, we can create effective steering control for this unique robot. In previous work, we demonstrated that pausing the motor at either the peaks or the troughs of its oscillation can create effective inertial turning, which we can turn into a controller and design into accurate waypoint following, as demonstrated by the blue path on this plot. So we've shown that we can control individual modules, but we want to be able to create potentially large structures out of these units, which would allow high-resolution oceanographic sensing, among other applications. To accomplish this, we need to be able to dock modules together and to undock them from one another. This is challenging even for conventional robots, especially in aquatic conditions, but especially so for a non-holonomic and underpowered robot like ours. In particular, I want to highlight three main challenges for modular self-assembly. 1. All parts of the Modboat are rotating, as is clear in this underview video. Docking to a rotating surface is not a trivial task. 2. Our discrete inertial controller only gives us control of the average orientation of the Modboat, because we need to oscillate to generate propulsive forces. But docking requires instantaneous control of the orientation. 3. In our previous work, we were able to accurately hit waypoints that are 20 centimeters in diameter. But docking requires that the target be another Modboat, which is only 7.5 centimeters in diameter. These three challenges make the docking problem a significant challenge for our system. So, before I discuss our solution, let's define what we mean by the docking problem. We want to find a solution for guiding a single mobile Modboat from an initial position to a docked configuration relative to a target Modboat. The target is not swimming and cannot adjust its orientation, although we do not assume it is explicitly stationary. We choose this subset of the problem because we anticipate that a Modboat subassembly will not be able to adjust its orientation to help with docking. Thus, the single mobile unit bears the entirety of the challenge of the docking procedure. Finally, we note that the Modboat has a preferred front direction. Thus, we want to be able to dock in any specific orientation, so that the final Modboat lattice has specific directions for each unit. So how do we solve this docking problem? We start by creating a passive docking system that has a large area of acceptance using permanent magnets. Each boat is given either a north or south designation, which maximizes the area of acceptance, and is given 4 docking points at the cardinal directions as shown. This creates a significant area of attraction around the Modboat, which can act to capture an approaching target, even if the approach vector is less than perfect. Now, because we can control the Modboat's orientation only in the average while swimming, we need to allow time before the dock when the Modboat deactivates its propulsion to focus on orientation. To achieve this, we define a cone-shaped approach region and a finite state machine procedure for docking. First, the mobile boat swims towards the point C, achieving sufficient distance along the approach line to the desired dock on the target. Then, it swims towards the target boat until it is both sufficiently close and turning in the correct direction. If it leaves the approach cone at any point, we abort and try again. At this point, if it has remained in the approach cone, the Modboat's velocity is pointing reasonably towards the target, and we can assume that it will drift the rest of the way and be magnetically captured. We can therefore shift our attention to stopping the rotation and setting the desired orientation for the dock. How can we control the orientation during this final phase? Well, instead of oscillating, we switch to treating the bottom body as a reaction wheel for the top body. It's not ideal, because the top body is far more massive, and the flippers do induce some translation, but it works. We use the PID controller shown here. The challenge, however, is that oscillations in the motor angle induce propulsion. Since we're no longer controlling swim direction, this propulsion will definitely be in the wrong direction and will prevent docking. So it's critical that the controller be underdamped. Except that means that response times are slow, which requires a more accurate approach vector that we can't guarantee. Our solution is to use gain scheduling for the PID controller. We start with an aggressive set of PID coefficients for speedy response, and then switch to a non-aggressive set when 90% of the orientation target has been reached to prevent undue oscillation. This graph shows the resulting performance. In blue, you can see that the gain-scheduled controller reaches the desired orientation much more quickly. Although it drifts much further in the long run, as shown in orange, in that short amount of time, it drifts much less. And so, as long as docking occurs quickly and obviates the need for further orientation control, this will be sufficient. In this video, you can see this control scheme in action. The Modboat adjusts its orientation by 180 degrees, with barely any drift occurring during the maneuver. Most of it occurs afterwards. So, does this strategy work? Yes, in 3 out of 4 configurations. We can achieve front docks and both side docks, where the Modboat spins by 90 degrees before docking, with over 95% accuracy. But we have less than 50% accuracy in achieving rear docks, where the Modboat needs to execute a full 180 turn before docking. Here's a video of the front dock. In this case, we don't need to turn before docking, but we do need to arrest any existing rotation. The approach sequence is shown here sped up, and the dock in real time. If you look carefully, you can catch the bottom body making its rounds as it stops the spin on the top body to allow the front-facing dock. And here's the side dock, where we need a 90-degree rotation during the drift period. In this case, we wait to transition to orientation control until the propulsive oscillation is already in the correct direction, saving effort and increasing response time. You can see the Modboat switch to orientation mode and execute the 90-degree turn incredibly quickly before it is magnetically captured. Now, in the previous videos, the target was fixed, but we can also dock successfully to a free-floating, but nominally not moving target. Performance is essentially equivalent, although the transition to orientation control must occur slightly further away. This is because the target can turn under magnetic influence, and this can result in a premature dock. As I mentioned, however, our method fails to execute 180-degree turns successfully. If the transition to orientation control occurs too far away, the propulsion that cannot be decoupled from the orientation control maneuver is sufficient to counteract the dock, as shown here on the left. If it occurs too close, however, there isn't enough time to execute the maneuver, and we end up with a side dock instead, as shown on the right. This restriction is unfortunate, but we can work with it when creating structures and associated assembly orders. Now, all of that was for docking, but modular self-assembly requires undocking as well. But that's what the tail is for. Although the flippers are completely enclosed in the footprint of the top body, the tail is not, and so by bringing their tails together, 2 neighboring Modboats can break their magnetic dock and separate without any additional actuators. Unfortunately, because the magnetic docks are passive permanent magnets, they can't be turned off. Thus, creating separation isn't enough to undock. We also need to prevent redocking. Moving the tails together slowly fails for this reason. The 2 top boats easily undock from one another, but then immediately redock as soon as the tails move away. Adding speed to the motion, however, adds enough impulse to cause the separated boats to drift out of magnetic reach. As it turns out, there's actually a sweet spot in between those 2 versions, where a successful undock occurs, but there is enough impulse that the redock is in a rotated configuration. Notice in this video that the rightmost boat has reoriented by 90 degrees after the undock maneuver. This fills in the gap left by our docking procedure. If a rear dock is needed, it can be accomplished by using a side dock and then reconfiguring by 90 degrees using the tail. In conclusion, we have shown that the Modboat, an oscillating swimming robot powered by a single motor, can dock to neighboring modules using control techniques from our prior work in 3 out of 4 configurations. We can also undock from neighboring modules without additional actuation, and we can use reconfiguration maneuvers to access the dock configuration that was inaccessible through normal techniques. Thus, the Modboat is now ready for modular self-assembly. Thank you for watching, and please reach out with any questions or comments.